right. Any other questions? There are a couple questions. One reason we're late getting started, folks, is if you're listening from home, is several people had questions before class got started with. Just have finished with them, and we're doing this. I don't think any of you have turned in anything yet. You've turned in a research paper, haven't you? Was it on Blackboard yet, or did you notice? Yeah, okay. I thought I got yours up there, but the things, because I got it done earlier, last week or sometime. But this weekend I got almost nothing accomplished school-wise that I wanted to. Friday was a disaster, almost, not totally, but largely. I had a real big issue on the way into work, so I was more than an hour late getting here. And then the dean called a meeting, and the meeting took way longer than it ever should have. So I got basically almost nothing done on Friday, which is usually my catch-up day to get all the grading done. And then when I got home, we were already supposed to have left town. My wife was not too happy with it, but fortunately someone came by, so we would miss her if I had been home on time, so that turned out okay. So anyway, we're out of town, and then I got almost nothing done while I was out of town. School-wise, I got a lot of stuff done, but nothing school-wise done. So if you had anything, I don't think this class had anything turned in over the weekend. I didn't get it graded, and I didn't get Blackboard updated, but I hope to get that caught up this week. Okay, and since Jasmine's not here, if that means she's not going to be here for the math team review, that gives me time to grade papers, so we'll see. All right, any questions before we get going? Okay, and like I said, the reason we late getting started was that two students had, and Dr. Bryant also had questions that took time between classes. I only had 5 minutes between classes, so. All right, and example 4, an initial value problem. Whoa, let me get my pen. Okay. Solve this. E to the 2y minus y cosine x dy dx is equal to e to the y sine 2x. Okay? And they give us an initial value, y of 0 is equal to 0. Okay. Since it's a first order differential equation, not even going to say linear. It's not, okay? Nowhere close. Okay, first order differential equation, it only needs one boundary value. Actually, initial value. Okay, and so we should be able to solve from there. What would be your approach? Okay, tell me how.
I would multiply e to the y. Divide by e to the y.
Okay, divide both sides by e to the y. So I'll choose to do that here, e to the y. Okay? Divide both sides by cosine x. Not sure I like that, but what you said was right. I don't like the way it's panning out. Anything else? Okay. Write it in differential form, which is just like multiplying by dx. Okay. Pure mathematicians hate to multiply by an operator, okay, but no, that's exactly what it looks like. So here we have, and let's clean up a little bit while we go. E to the 2y over e to the y is e to the y minus, let's see, how do I want to write this? I may want to write this minus y(e) to the minus y. Is that okay with you if I do it that way? By that. Okay. And this will be my dy equal, and I think I want to do something else with that cosine 2x. Any ideas what I might be able to do as a simplification? Let's put this a little beyond having any trig identities in it, I think. No. What's that? Okay. Here's what I do sometimes. Do you remember this one? Goodness gracious. Say sine and write what I was going to do, sine of. Okay. Sine of alpha plus beta. Do you remember how that goes? Okay. Sine alpha cosine beta, ring a bell, plus cosine alpha sine beta. Okay, by that, I can tell you anything, couldn't I? Huh?
I don't remember them at all.
Okay. Well, what if alpha is equal to beta? Then this would be sine of 2 alpha, wouldn't it? Okay. And that would be sine alpha cosine alpha, right, if they're equal, plus cosine alpha sine alpha, so that would be 2 of them. Okay? So then what would be sine of 2x? Sine x, cosine x, but with a 2 in front, right? Like that too. Over cosine x, which then get rid of the cosine x's, right? And then, written in differential form, that would leave you a dx there, right? Or multiplying both sides by dx, okay? Does the same thing, right? All right. Now let's see what we can do about integrating both sides. I think I can even do that first one. Say again? E to the y minus. Now, that's kind of a real pain in the neck, isn't it? What are you going to have to do for that one? I think I'll write it down here. Integral of y e to the minus y dy. What technique would you use for that? Integration by parts. I believe you're right. How would you start that? Let u equal let that be the y one, and dv equal e to the minus y dy. Kind of ring bells? Then yeah, du is equal to what? Just differentiate both sides. dy. Right? Okay? But on this one, you have to integrate both sides. So your v would then be negative e to the minus y. Wouldn't it? Because if you take the derivative of that, you're going to wind up with what you have. Okay. Still not there yet. Where do you go from here? That's just a setup for integration by parts. Now we get our answer. The integral of y e to the minus y dy is equal to, remember how it goes? Okay, u times v. All right, so that would be minus y e to the minus y. Okay, then we do a minus the bottom line here, these two. Well, it's going to be a minus, but that has a minus, so that's going to be a plus the integral of e to the minus y dy. Right? And we can do that now. This will be minus y e to the minus y. What's the antiderivative of e to the minus y? Say again? Right. Okay. So that's what that one is. But notice there's a minus in front of it, so that's going to change both of these to pluses. Okay? So let me go on and draw through this and write plus y e to the minus y plus e to the minus y. That's equal to, I'll bring the 2 outside the integral. What's the antiderivative of sine x dx? Antiderivative of sine x dx. With a negative, yeah. Derivative of sine is cosine. Antiderivative of sine is negative cosine. Okay? Because derivative of cosine is negative sine. So that would be a minus 2 cosine x. Okay. Now, plus c, because all those were indefinite integrals, right? So you got to have a plus c in there. But now we use our initial value. So plug in x equals 0, and when you plug in x equals 0, that's going to make y equals 0. So what do we get? I need to, here's my equation right here. It's just sort of funky because it's sort of rose and fell there. So everywhere that we have an x, we're going to put a 0. Everywhere we've got a y, we're going to put a 0. So what's e to the 0? 1 plus that 0, that y is going to make the whole term 0, right? And the next one? 1 again, okay? So the left-hand side's 2 so far. This is equal to, what's cosine of 0? So there's a minus 2 here plus c. So what have we got? 2 is equal to negative 2 plus c. What do you reckon c is equal to? 4. So our answer is, where will I write it? Yeah. I think I'll write it up here at the top, if that's okay. E to the y plus y e to the minus y plus e to the minus y is equal to minus 2 cosine x plus c plus 4. Now let's see if there's, I don't think there's any way to make that any simpler. So let's see what they got for their answer. E to the y plus y e to the minus y plus e to the minus y is equal to 4 minus cosine 2 cosine x. Yes, that's what we got. Got it? Any question on that? Okay. Now this next little thing is use of computers. And if you got them, use them, okay? If you got a package that will do these calculations and draw the pictures for you, by all means use them. There's nothing wrong with that. But I don't see too much reason to go into huge detail here. But I do see something we can do at the top of 51. So let's just move there. All right, to erase what I got? Okay. All right. Here's an initial value problem. dy dx is equal to xy to the 1/2. Okay, way back in section 1.2, example 4, they told us the answer to this one. They don't need to tell us anymore because we can do it, can't we? Same initial condition we had before. How would you do this? Say again? Okay, how would you do that? Okay. Well, you know what I'm going to do, if it's all right with you. But I don't want to do it if it's not, okay, is write this as y to the minus 1/2 over here. Would you be okay with that? Okay. So that'll wipe that out there and write it there, and then the other thing. Yes, okay, multiply by dx, okay. That's how I think of it too, but I'm not supposed to say it that way.
What are we supposed to say?
Write it in differential form. I don't know if the book cares, but so anyway, there it is. So what we have is y to the minus 1/2 dy is equal to x dx with those conditions. And now what? Integrate both sides, and what does that give you? Okay, negative 2y to the 1/2 is equal to, second, x squared, how about over 2, plus c, right? Now, is that right? I don't think there's a minus on there, is there? Huh? Okay. I think that's right now. Okay? So let's plug in our initial condition. And what do we have? 0 equals 0 plus c, so c is equal to 0. I'm pretty sure, right? So let's see if we can write this as 2y to the 1/2 is equal to x squared over 2. How about us writing that as 2y to the 1/2 is equal to x squared. Or the way they wrote it is this way. They said, before they did the plus c, they wrote it as y to the 1/2 is equal to 1/4 x squared, right? Well, I guess, yeah. And then they added the plus c, and then they squared both sides. Y is equal to 1/4 x squared plus c squared. That's the answer they got. Now, if you put the c in too soon, you could have had something, but then you would have had a 2c, but then change the c and make it c again. If you wait too late to do it, however, you may not quite get the right answer. For instance, you really need to introduce the c before you square both sides. Because that does make a difference. And this is the solution we got before. They gave us before, now we calculate it ourselves. Okay. So, with c equals 0, though, who cares? Okay. C is 0. So, y is equal to 1/4 x squared. That 1/4 x squared, which is y is equal to 1/16 x to the 4th. And I think that's actually how we used it way back. Okay? Now, however, that's not the only solution. Okay? Certainly that works with this initial condition. If you take the derivative of this, dy dx would be 1/4 x cubed, right? And take that 1/4 x cubed, take the square root of that. 1/4 x cubed, that's what dy is. Multiply that by x, and you have y prime is equal to 1/4 x cubed. Okay. And y to the 1/2 is equal to 1/4 x squared. So sure enough, y prime is equal to y to the 1/2 times x, which is what we had at the original. But that's not the only, and that works when x equals 0 and y is equal to 0. But guess what else? If y is equal to 0, period, okay, then y prime is equal to 0. So dy dx 0 is equal to x times 0. Y to the 1/2 is 0. That also works, okay? So you actually have a singular solution that mixes in with this one. But you see why when we divided both sides by y to the 1/2, we lost that y equals 0, because if y is equal to 0, we can't do that. Can we? So you actually have, so this solution we got this way, we have to exclude y is equal to 0 from the solution because we divided by 1. You can't ever divide by 0. But then if you go back and put it in, because y equals 0 also satisfies that, then that's why they listed it as a piecewise defined function. They said y is equal to 0 when x is equal, actually, they say when x is less than a, okay, and it's 1/16 x to the 4th, anytime x is greater than or equal to a. Okay. Which, I'm sorry, that's not quite right either. It's see, this is getting a little wacko here. I mean, they introduce another constant a in the same place, or almost, not quite the same as they did the c. It's just I'm not going to worry with the rest of that. It almost looks like okay. That, to me, they don't give an adequate reason where the a comes from. They just sort of throw it in there. For any choice of parameter a, blah, 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 piecewise defined function works. Okay? Well, the thing is, where did that come from in the first place? Our initial value problem, what we came up with, worked. I'm not going to worry with it. They don't really do a good enough job on that. Now, there is something else coming up here that I think is worthwhile noting. Sometimes when you're doing a differential equation, you might not ever be able to get what the value is. For instance, dy dx is equal to g of x. Now, if that's all they gave you, and you don't know anything more about that function g of x, and they also give you the initial condition, y of x0 is equal to y0. Okay? Very generic here. And if that's defined, this differential equation is defined on some interval I, And your solution, basically, dy is equal to g of x dx, and integrate both sides. Y is equal to the integral of g of x dx. If you don't know even what the function g of x is, that's still true, okay? Except you sort of have to go back to your fundamental theorem of calculus part 2, which says y is equal to the integral from x0 to x of g of t dt, okay? And then plug in when x is equal to x0, y is equal to y0. So it gives you y0 is equal to, so let's do plus c here to keep it general. That would equal to c. Okay? So your solution is y as a function of x is equal to, and they write the y0 first with no real good reason. Instead of the c in front, behind it can go in front, plus the integral from x0 to x of g of t dt. Okay? And that is sort of a generic solution. If you can integrate g, do it, and you got your answer. But if you can't integrate g, you can integrate numerically, or however it is, and come up with an approximate solution. Okay? Because you see, when x equals x0, this goes to 0. That's why y is y0. Okay. Now, don't know if we're going to use that or not. My expectation is we probably will, but let's do example 5. Solve this. dy dx is equal to e to the minus x squared, okay, with an initial condition y of 3 is equal to 5. What would be your first step? Say again? Yeah, well, do your thing with the dx first, okay? Write it in differential form, multiply by dx, however you want to say that, then integrate, okay? Can you integrate e to the minus x squared dx? Neither can I, okay? That's one of those transcendental functions or something like that. There's just no way, okay? We don't have the tools to do it, okay? But what we can do is y, that's on this side, is equal to, from what we just did, the integral from 3 to x, we got that 3 from, that's the lower value here, e to the minus t squared dt, and when you plug in x equal 3, you get y is equal to 5. This will be 0, so y is equal to 5. So you get, so you get y is equal to 5 plus the integral from 3 to x of e to the minus t squared dt. Okay. Now that is a solution that for various t's you can put in, you can get numerically integrate that and come up with it. By the way, does that look at all familiar in any way, shape, or form? You ever seen anything kind of like that before? Basically, this does your bell curves. So when t goes to infinity, that's going to 0. Okay? When t is at 0, you're basically at your max. And so that gives you basically a normal distribution. There's got to be some other weasel words in there, constants and other things, like 1 over square root of 2 pi or something like that in front. But that basically is going to give you something that looks pretty close to your normal distribution. Okay? All right, so you get y of x. I should have left the x here. Y of x is equal to 5 plus the integral from 3 to x e to the minus t squared dt. And guess what? We can just leave it like that. There's nothing else we can do. We can't integrate that, so leave it in that form. All right. That finishes 2.2. Homework exercises: do any of the odds 1 through 21, any of the odds 23 through 27, do 29, do either 31 or 33 or both, do either 35 or 37 or both, do either 39 or 41 or both, do 43, do any of the odds 45 to 49. And then you're welcome to look at the discussion problems. I don't think those typically have answers in the back of the book, so you don't need to sweat it. Okay? Okay. Sometimes some of the discussion questions, I don't see any in this case now, or the mathematical models or the computer lab assignments or something might lead you to maybe another paper topic or something like that, somewhere to continue looking. You can look if you want to. I was trying to think if I could think of a good paper topic for that would go along with 57. And if I'm not mistaken, the curve you see there in 57 is very, very close to, if not exactly, goodness, I can't think the name of it now. We just did it in class earlier in either Cal 2 or Cal 3. We actually did that. I think it was Cal 1, Cal 2. I can't remember it, but anyway, catenary, I think is what it's called. Yeah, I believe that's what it's called. That shape is called the catenary. All right, so that finishes separable variables. Ready to move on to 2.3, which is linear equations. head's stopping up again. I'm having trouble breathing, but let me see if we can finish it. Continuing the quest for solutions of first-order differential equation, we'll now consider linear equations. Linear differential equations are especially friendly family of differential equations in that given a linear equation, whether first order or higher ordered, there will always be a good possibility we can find some sort of solution in the of the equation that we can examine. So, blah blah. Here's our first, the definition, linear equation. Okay? First order linear equation of the form of this. A sub 1 of x dy dx plus a sub 0 of x y is equal to some g of x. All right. Now, this is, in a sense, the most generic form of a linear differential equation. Now, why do we say it's linear? Well, in first order linear at that. First order because the maximum derivative is dy dx first derivative. Okay. Linear because the dy dx shows up by itself in its term. Y shows up by itself in its term, and everything to the right side of the equality is just a function of x. Now, you can have a coefficient function of x here and a coefficient of a function of x there, and any function of x there. They don't have to be in any way, shape, or form linear in x. Who cares? Okay? But this is linear in y. Now, what you couldn't have, dy dx squared, or to the 1/2, or to the 3/2, or to anything other than first power, linear. The y, you can't have a squared, or a 1/2, or any other power of y except 1. What's more, you can't have a dy dx times a y, or a y times a dy dx. That would make it nonlinear. So, with some coefficient of x, function of x, that's no problem, dy dx, with some other coefficient function of x times y is equal to any other function of x, that's fine. And these could be weird, wacko functions here of x. Sine functions, exponential functions, log functions, power functions, whatever you want to have. They don't have to be in any way, shape, or form linear. The y's have to be linear. So that's what makes it a linear function. It's a linear first-order differential equation in y. Now, what we're going to do to it, that's your generic form. Your standard form, however, is going to divide by a1 of x. Divide by a1 of x. Divide by a1 of x. Now, obviously here, a1 of x cannot equal to 0 anywhere on the interval that you're allowing it. Because guess what? If a1 of x was equal to 0, you wouldn't have a differential equation, would you? Because that term would be 0 anyway. So that isn't a huge requirement. And what we're going to do then is rewrite this as dy dx plus p of x. Now, I really don't like that they do this, but it's across the board. Everyone does it. To me, capital P of x means a polynomial of x. Not here, it doesn't. That doesn't need to be a polynomial function of x. It's just typically what they name it. That would be P of x, y is equal to, and this, it's got to be some f of x. It doesn't have to be, it can be a rational function. In fact, it looks like it almost has to be a rational function. but it can't be, but get rid of that a1 of x altogether. Don't even mess with it. That's your standard form for a linear differential equations. Okay? Now, what's required of it? We seek a solution for that on some interval I. Okay? Now, guess what the interval I must have? Interval I must be any value of x that keeps this a1 of x not equal to 0. Okay? So if any a1 of x would become equal to 0, that value x can't be on that interval I. Pick some other, Now there may be other requirements, but that's one thing about I. You have to avoid any x's that would make that a1 of x 0. Okay? There may be other restrictions on it, but that's one. Okay. Now, on that interval I, and this is almost saying the same thing, p of x and f of x must be continuous. Okay? Can't have any jump functions or anything else in here. So, p of x and f of x continuous. Okay. So let's see. dy dx plus 2xy equals 0. Linear or not? Yes, definitely linear. Okay? dy dx is equal to y plus 5. Linear or not? Yeah, that would be linear. Just subtract y from both sides of the equation. You have dy dx equal minus 1 times y. Dy dx minus 1 times, minus 1 times y is equal to 5. Perfectly fine. Okay? Both of those are linear differential equations. Now, the first of these, this one here, subtract this from both sides. That circle. That's the way to go. Don't mess around with linear technique. Use circle. How about this one? Not so. Okay? You can't separate the y from the 5, okay, by multiplication or division. And it may be that someone can figure out a solution for that, but we're not going to mess with it. That's just not so. So this linear technique may really work best in some cases. Wait, they say that's not. Let me see. They say both of these say that one's separable too. Let me see. Yeah, I'm sorry. dy over y plus 5 is equal to dx. Yeah, that's separable. Sorry about that. You know what that would be? Worked it out, huh? If you integrate both sides of that, what do you get? Yeah, well, absolute value y plus 5. Okay. about this one. Looks pretty similar, doesn't it? dy dx plus y equal x. Is that separable? No, it is not. Okay? So even though it's simpler looking than some of the other forms, not separable. Okay? At all. But linear it is, and it's very easy to do in a linear form. All right. So how do we go about doing this? The method for solving this type of an equation of this form right here hinges on the remarkable fact that the left-hand side of the equation can be recast into the form of the exact derivative of the product by multiplying both sides of that equation by the function of what they call mu sub x. Okay? And they say it is relatively easy to find a function mu of x. And here's what our goal is with a linear equation. Okay? Here's what we want. Okay? Now, don't worry about what the mu sub x is now. What we want to do is find it. Okay? But tell me something about that mu sub x. Taking a derivative of that, what would you get? Product rule. Mu of x times what? Y prime of x, okay, plus okay, plus what? U prime of x, y of x. Shock! Okay, if I can ever get it written. All right. Now, that's always going to be true. Okay? Now, let's go back to this. Dy dx plus p of x y equal f of x. Okay. What were to happen if we said that mu prime of x d mu dx, mu prime of x, was equal to mu times p of x. Okay? If that could be the case, then we have a, if we could say that mu prime d mu dx is equal to mu times p of x. Okay? If you could make that happen, then what you have here is let's just say this is our target right now. If we can make that happen, let's see what happens to the rest of it. Okay, I think that'll be better than trying to convolute around to do it. Okay, so this is what we're shooting for. Is that equation right there? D mu dx is equal to mu times p. D mu dx is equal to mu times p. That's a function of x as well. Mu is a function of x and p is a function of x. All right. Let's see about solving that one. Okay. Now, I can almost hear it because I feel this every time. I feel like we're running around in circles. Okay. Well, what if there's a mu that this happens? Well, let's see if we can find the mu that make it happen, then it would happen. And it feels like you're just going around in circles almost, or what they call circular logic. This is differentiable, I mean, separable. So this would be d mu over mu is equal to p of x dx, right? If that equation can be found, pretty straightforward, right? Any problems with it? Okay. Well, let's integrate both sides, just like we do with separable equations. What does the left-hand side become? Say again? ln. ln of mu is equal to the integral of p of x dx. Now remember, our original requirement was that p of x cannot be, has to be continuous. Can't have any gaps, jumps, discontinuities in it. Has to be continuous. Okay? So if that's the case, then we can integrate it. That's all that's required for integration, is to have a continuous function. So we certainly can do that. Okay? If that's the case, then mu of x, let me back off just a little bit, because I know this is old hat to me, but I want it to be reasonable to you. Okay, remember that the inverse function of ln is what? Eta. Okay, so let's take an e to both sides of this. Okay, and then what we've got is mu of x is equal to e to the integral p of x dx. All right, suddenly we've run around in circles and we got something, and we say this is what we want. Okay? If we can integrate that to u of x, whatever it is in our original function, integrate that, whatever that integral turns out to be, have e raised to that value of x, okay? That's going to be our u of x, okay? And hopefully it's going to be a relatively simple function, okay? We sure hope it will, okay? And we're out of time. All right, we'll pick up there next time, okay? Where were we? Right here. We call that the integrating factor, okay? And we will pick up with this right there next time. Okay, did we get far enough to do anything in this section? I kind of think not. We didn't do any examples, so we'll not have any new homework exercises there. We'll pick up there and go. All right, good deal. We'll see you Wednesday.